In the first session, we try to understand a transmission line from basic concept and also some physical pictures. In the second session, we have a tool called telegrapher's equation to model the problem. Now, I want to give you a few characteristic examples to emphasize the concept and also start to use the result we derived from the last session. For example, in the transmission line, we care a lot about the transmission of a signal. So I want to introduce the concept of dispersion first. So in a material or structure with dispersion, different frequency components of a wave will propagate at different velocity. In particular, if you send a wave with different frequencies inside, then the phase velocity could be different for different frequency components. And so if you have a phase velocity that is a function of frequency, then this means that the structure or the material is dispersive. For example, if you have a pulse that consists of different frequency components, and you propagate this signal pulse into a dispersive system, and different frequency components denoted by different color here will be propagating at different speed. So this means that not all the frequency components will be arriving at the same time. So in the end of the system, the pulse will be broadened and the amplitude could be reduced. And this causes distortion to the signal quite often that this is an unwanted result in the system. And you design a transmission line, sometimes you want to avoid this kind of pulse distortion due to dispersion. Now, let's look into several examples. For example, when we design a transmission line, the first rule could be that we want this transmission line to have very low loss. So we look into the loss of a circuit. We understand that the loss is primarily from the ohmic loss. So if we set R or G equal to 0, then this transmission line will be a lossless transmission line. So let's put R and G equal to 0 into this gamma expression. Then you end up having a gamma that is pure imaginary. So this means that the attenuation constant alpha is equal to 0. So this means that indeed this transmission line is a lossless transmission line. So for this wave propagating over some distance, the amplitude is not going to change over time and over distance. And the propagation constant basically is beta equal to omega multiplying with the square root of LC. So if you calculate the phase velocity based on this expression, you find that the phase velocity is not going to be a function of frequency. So this means that this lossless line is not only lossless, but also dispersionless. There's no dispersion in this transmission line. This is the ideal situation where you don't have resistance or conductance in a line. But if you allow this line to have small resistance or conductance, then there will be a little bit of ohmic loss. So let's do this small loss approximation in this gamma value and just retain the first order term in this Taylor expansion expression. So you have this result if you just keep the first order terms from the Taylor expansion of this gamma. Then you can separate alpha and beta from this expression. For alpha, you do have a small value that is proportional to the resistance and also the conductance. This means that if you propagate a signal on this transmission line, the signal will be attenuated a little bit during propagation. And because this line has alpha value, so if you pick up the the imaginary part of the gamma, then you can deduce the propagation constant. And this propagation constant, based on the first order approximation, this propagation constant is the linearly proportional to the frequency. So if you do a ratio of this frequency over beta, you'll be able to deduce the phase velocity, which is not quite a function of frequency. Remember that we have some approximation here. It just tells you that in general, if you have a very small loss associated with the transmission line, then this line can be considered as a dispersionless transmission line. And you can see a little bit struggle here to make a conclusion, because this is the approximation, but not the real situation. In some real situations, you cannot avoid R and G in the transmission line. But if you design your RLGC to satisfy this condition, then you can still have a dispersionless or distortionless line. If you set this condition into the calculation of this gamma expression, then you end up having this expression as the imaginary part of gamma. And then you multiply this with this, then you will get a real part of the gamma. The real part of gamma is going to tell you the attenuation of the signal, which is given by R multiplying with the square root of C over L. And so in real situation, the signal will be attenuated over time and over distance. Then the propagation constant based on this expression is given by omega multiplied with square root of LC, and you have a linear relationship between beta and omega. So the phase velocity now is not a function of frequency. So this means that if you send a short pulse signal through this transmission line, there won't be dispersion to distort the signal. So given this condition, you can design a distortionless transmission line. 所以呢，在这个小节里头，我讲了几个特征的例子。那在刚开始的时候呢，我介绍一个观念，什么叫做色散？色散的意思就是在一个系统里头，可能是一个物质里头，或是一个这个 transmission line 传输线的系统里头呢，你如果送一个讯号，这个讯号里头有一些不同的频率在里头的话。那譬如说，你如果送一个脉冲的讯号里头就有不同的频率在里头，这时候呢，不同频率的这个能量跑的速度会不一样，那这个系统呢就是有色散。那同样的，在一个 transmission line 里头呢，你也会有损耗，这个损耗主要是来自这个 ohmic loss， 来自这个transmission line 里头的电阻跟电导。那这个 ohmic loss 呢，会造成这个讯号在这个 transmission line 里头传播的时候衰减。但是呢，如果说你在设计这个 transmission line 的时候呢，允许这个 RC 等于 LG 的话呢，这时候虽然有些衰减，但是呢，你的这个讯号呢不会失真，也就是这个 transmission line 呢还是可以做到没有这个色散。那就是这是一个条件，你可以做得到的。那这是几个特征的例子，在刚刚介绍的这个 transmission line 里头可以进一步的考量跟理解。OK， 谢谢。